Then what does it mean to have stream reservation? So, and here I really try to start at the very beginning. I do not want to bother you with OSI layers. You have heard that often enough, I guess. And I think it causes more confusion than bringing clarity. But I think it's interesting to have a quick recap about what is an Ethernet packet. So in every packet that we send on a network, no matter if it's Dante, AVB, or whatsoever, we always have a destination MAC address. So we have an address identifier at the very beginning of the packet, which says where this packet is sent. Then we have a source MAC address. That's the second part here. So this is an identifier that is unique for the sending device. And then it goes further. We have a VLAN ID. So we have a identifier whether it's a VLAN or not. So also interesting to know that every AVB stream gets assigned to a VLAN. So we have a VLAN identifier. And then we have the ether type. So until here, there's nothing special about AVB. This is common for any IP packet, for anything that you will see on a network. The ether type defines whether this is an IP packet, or in case of AVB and Milan, we have a special identifier for making this an AVB packet. So our network infrastructure, our switches, can differentiate whether this is high priority AVB or if it is IP or any other thing. And then after that, AVB-specific things will follow, which we do not need to go into, but this is basically where you would find the timestamps and the audio samples. This is how every Ethernet packet is structured. And this is also what gives us the advantage that if we have unique MAC addresses here that can clearly identify a stream, the switch can go in very early and identify this is AVB, I need to handle that in a special way. What is a stream? A stream is basically a sequence of many of those packets. Yeah? We send per stream, we send 8,000 packets per second. Each packet contains 6 samples per audio channel. So this ends up with having a really high packet rate, and we can have 150 of those streams. Yeah? So just to have that clear, a stream is just a continuous transmission of these Ethernet packets. So now, what is special about AVB? First thing, we have the so-called multicast address allocation protocol. So every device here requests a unique multicast MAC address. That's the very first thing we want to put into our Ethernet packet. If every stream gets its unique multicast MAC address, then we have a pretty simple scheme in the switch to say, okay, I need just to look at this destination MAC address, and based on other information, I can then decide where to send it. Yeah, but this is always a unique thing for every stream. So that's the first fundamental step to take here. Every stream has its own multicast MAC address. Then the stream reservation protocol, and I'm really trying to keep it simple. Practically, it's of course much more complex, but the basic scheme is something like the talker goes in. Here, in this example, we send a stream out from the mixing desk. So the mixing desk would register its stream on the switch. So all switches in the network know what streams are around on the network. Then a loudspeaker, for instance, can go in and say, I want to receive that stream from the mixing desk. And only if there is enough bandwidth, this mixing desk will start streaming. It will not send anything to the network if the switch and the whole infrastructure cannot guarantee that this bandwidth can be handled. And then it can also make easy decisions to say, okay, this is a loudspeaker that requested that stream, so I forward it. If it's not requested, it will not be forwarded. So we do not flood the network with multicast. We have a very clear rule where we send packets, only to those who requested. That's stream reservation presented in a simple scheme. Now, this is a more complicated topic about queuing and shaping, so I will keep this very short today. But in principle, the thing I want you to understand is that we have special mechanisms now in the switch that allows us, because we have this multicast MAC address range, special for AVB, we can identify what packet it is. So we say, okay, this is an AVB packet. It is a MAC address that got a reservation, so I allow it to get in. If it's not reserved, I would not even allow it to get into the switch. Then I can have different queues, so it's like having one lane where I put all the high priority traffic in, which is our AVB traffic. And there might be some other control stuff coming from a laptop, some maybe OCA remote control stuff. That is not as time critical as delivering the audio. So we put that into the low priority queue. And then there is these so-called shapers that regularly inspect these queues and send out traffic in a very regular intervals. Now, I mentioned already that it's often heard that AVB steals away bandwidth from other applications. So the way this works is that only the bandwidth that is used for the streams that get connected and reserved is used. So let's say you have 48 channels on a link and you make reservations for that, then only these 10% are reserved for that stream. The other 90% of your gigabit link, which would be 900 Mbit, being just available for control and other stuff, still is available. So it's still a decision of the user how many streams you connect and how much bandwidth you have here. Now, another way to look at this is this 75% thing. You can see this more as a limit. If you have connected already 360 channels and you use this 75% for AVB, and now you would try to add another stream, the switches would say no. They are not allowed to reserve more bandwidth than these 75%. So this also implies that these remaining 25% are still guaranteed to be available for control. So it's not only about the guarantee for your audio data, it's also about a guarantee for all the other applications. And if you really need to, you can also adjust these thresholds. That depends a bit on the API of the switches, but in theory, depending on the vendor, you could adjust this value. That's possible. Yeah? Maybe also as a little tool when you plan a network, here's an overview how much bandwidth is really consumed, depending on the sample rate you use. Typically it's 48 kilohertz or 96 kilohertz. Then you can put a different amount of channels into a stream. Yeah? A microphone would typically be a single channel stream. If you have something like a stage box, it's more likely that you have streams where you have 8 packets of 8 channels and then multiple streams of those. In an 8 channel, just as a rule of thumb, maybe a number to remember is that you are around this 16.5 Mbit per second for an 8 channel stream at 48 kilohertz. So that's useful to have available as a rule of thumb, and it approximately doubles, little bit less, but that's how you can also plan your network and the required bandwidth.